material modeling. And vision transformer is very similar to the transformer, but has the following three major improvements: patch embeddings, class token, and learnable positional embeddings. The most important one is patch embedding. It patched the input sequence as two-dimension patches. The complexity per layer of vision transformer is much smaller than the transformer by dividing by the patch length. So it costs less memory than the transformer. At first time I used the transformer and my Python tried to allocate 45 GB memory for my model. It is unacceptable, so I turned to vision transformer. And I see the number of the parameters in the final test, only 5 or 6 or 7 teams use the transformer-based models because our numbers are much bigger than other teams. So if you want to use a transformer-based model with a higher sample rate, I suggest vision transformer as a backbone to save resources. Okay, next is our model overview. And here is input BT sequence. First input to the linear projection of flattened patches model. In this module, the patch embedding and the class token and learnable positional embeddings are applied. And the next steps are just the same as for the transformers. So the improvements are just these two modules. And scalar inputs are added here after the token passed the transformer encoder modules. And here is our test results. You can see most models perform well, but only material D performs much worse than other teams. So here is some reasons. I think one of the possibility is the lack of inductive bias. The inductive bias is the set of assumptions that the model used to predict outputs of given input that it has not encountered. The inductive bias of vision transformer is smaller compared to the convolutional neural network and recurrent neural networks. In the vision transformer-based approach, only the MLP layers are local and the translation invariance. So that's why it is harder to train, and it needs sufficient data for training. And in model of material D, only 500 data points are used to train. It is my fault, not the shortcoming of the vision transformer. Right. So maybe use transfer learning for material D is a better choice.
Yeah, maybe you can give it a try now. Like now you have the data and you have you can do a verification, and that's yeah. As you said, it looks like if you pre-train it a little bit with other materials, you'll be fine for dealing with these.
Yeah. And yesterday I heard some teams use FFT and LSTM to model. I think the inductive bias of LSTM and the recurrent neural network assumes that there is a relationship between the time steps on the sequence order, but the FFT may damage this relationship. So I think if you want to use FFT as preprocess, maybe convolutional neural network or MLP is better.
Yeah, so these are great arguments. I really look forward to some teams maybe as a further study can study this, because honestly, my team we did something and we never really tried to explain why. And looks like these are some explanation why if you do FFT, maybe LSTM is not a bad choice. Maybe CNN or other networks a better choice. Or if you go with the Vision network. So yeah, great. So these are great questions you raised.
Yeah. And also using means and the standard deviation to normalize the data is also an inductive bias. It assumes that the training and test data follows the same distribution. But this assumption may not work so well when
This
it
may not
comes
be true.
to real life challenge.
That's right. Yes.
And we also find that similar materials can share models. We try to train the material 77 and 78 in just one model. And the average of the 95 percentile error is about 8%. But when it comes to 27, 30, 49, and 87, it doesn't work so well. It may be caused by the normalization of means and standard deviations, I think. So I'm still considering how to deal with this. Maybe
I
we
guess.
need a
go ahead.
Maybe we need a new normalization method when multi-material are used to train, or bigger network or something, I think.
Right. Yeah, you raised a very interesting topic. Usually manufacturers produce new material based on their existing material. Like we know 3F4 is a fine tuning of the F3. So if any of you, that's the purpose of doing this challenge, because in the United States we don't have access to companies. These materials are usually not made in the United States. So a lot of them are in China, some of them are in Europe, in Asia and Japan. So if any of you guys have access or have contact at these companies, and maybe we can close the loop. Like you have trained model, you have good understanding of the material, and then how does this tie back to chemistry and the way they make materials? And maybe we can use the models we develop to guide the material development. That would be really, really exciting. And in the United States, we have limited resources in doing that.
Yep. And that's my presentation.
Okay.
Thanks for the MagNet challenge team, and thanks for the listening.
Yep. Thanks. Any questions? Comments? Okay. For the sake of time, we have like 8 minutes. We don't want to run for too long. So we'll move on to the final team, CEO Boulder.
Okay.